Hello, everyone, and welcome to the first part of our deep dive into electronically commutated motors, commonly known as ECMs. These motors, which first made their mark in the industry between 1977 and 1991, completely revolutionized how we approach HVAC efficiency and airflow management. Today, we are going to explore the theory behind how they operate, and then we will walk step by step through the diagnostic procedures you'll need to troubleshoot them effectively in the field. To understand ECMs, we first need to look at the core principles of motor control. The motor speed is directly controlled by the drive's output frequency, while its torque is adjusted by varying the output current to meet specific load requirements. Instead of using physical sensors, the drive senses the rotor's position and RPM by monitoring the motor's back electromotive force, or back EMF. This intelligent drive not only optimizes overall performance and efficiency, but also actively protects the motor from damage during abnormal load conditions. Let's look inside the motor drive. The drive utilizes high-current, high-voltage power switching electronics. Incoming AC power first passes through a power factor correction inductor and a high-frequency EMI filter to clean the signal. It is then converted to DC by a full-wave bridge rectifier and smoothed by a DC capacitor. The brain of the operation is the microprocessor control circuit, which dictates the action of the solid-state power switches for phases A, B, and C, effectively managing the power sent to the motor stator. So, how does this electrical commutation actually work? Imagine the solid-state switches as mechanical gates. The microprocessor closes specific switches to allow current to flow from the negative terminal through two legs of the motor windings and out to the positive terminal. By rapidly opening and closing these switches in sequence, the drive creates a rotating magnetic field. The speed at which these switches operate generates the specific frequency in hertz, which in turn dictates exactly how fast the motor will run.
Now, let's get into troubleshooting an ECM2 blower motor that simply will not run. Step 1 is to place a jumper between the R and G terminals on the motor control board and check if the fan red LED illuminates. If it doesn't, you move to step 2 and check for 24 volts AC between the R and B terminals. If you don't have 24 volts there, your problem is upstream. You'll need to check the power supply, the transformer, or the fuse. If you do have 24 volts, you proceed to step 3. In step 3, we are looking for a DC voltage signal. Check for 4.0 volts DC between pin 15 and pin 3 on the low voltage plug. If you read 7 to 8 volts DC, the board is sending the signal, so you should check the motor winding resistance. Remember, ECM2 windings test just like a three-phase motor. All three legs should have the exact same resistance. If you read 0 volts, or a low voltage that jumps back up to 7 or 8 volts when you unplug the harness, the motor module itself is likely dragging the voltage down and needs replacement. Moving to step 4, verify that 24 volts AC is reaching the motor at pins 12 and 1. If it's missing, you have a broken wire in the harness or a bad control board. If the low voltage is good, step 5 requires checking the high voltage power plug at pins 4 and 5. Keep in mind, furnaces use 120 volts AC and require a jumper between pins 1 and 2, while air handlers use 220 volts AC. If the line voltage is correct and the motor still refuses to run, verify the winding resistance and replace the motor module. Step 6 helps isolate the control board from the harness. Unplug the 16-wire harness and check for 7 to 8 volts DC directly at the board's pins 15 and 3. If the voltage is missing, the board is bad. If it's present, your harness is faulty. Finally, step 7 addresses systems with White Rogers ignition modules. By jumping G in to G out, you bypass the module. If the motor suddenly runs, the ignition module has failed. If it only runs when you adjust the jumper to the metal pins, you likely just have a dirty connection. To make this process much easier, you can use the ECM2 Troubleshooter Kit. This diagnostic board plugs directly into the 16-wire harness to visually verify the signals being sent to the motor. After disconnecting power and field wiring, you plug it in and power the unit back on. The red R LED should light up immediately, confirming 24-volt power, and the green CFM LED should flash. You can then toggle dip switches 1 through 8 one at a time, verifying that the corresponding LEDs light up in sequence. The Troubleshooter Kit also allows you to simulate thermostat calls. By jumping the R terminal to the various low-voltage terminals like G, Y, or W1, you should see the corresponding LEDs light up on the test board. However, you must be aware of equipment-specific exceptions.
For instance, on furnaces and packaged gas electric units, the W2 LED might not light up because of the ignition control's normally open switch. Similarly, on air handlers, the W3 terminal is used instead of W2. If you don't have the full troubleshooter board, you can perform a quick go, no-go test using a 4-wire test cable. By simply connecting the red wire to R and the blue wire to B, the motor is commanded to run at continuous fan speed. If it doesn't, and you have verified your voltages, the motor has failed. Another feature to note on these systems is the cooling off delay option. This utilizes an electronic time delay relay to keep the indoor blower running briefly after the outdoor condenser shuts off, which extracts the last bit of cooling from the evaporator coil. ECMs aren't just used for indoor blowers, they are also used as outdoor fan motors. If an outdoor ECM fan won't run, start with the basics. Ensure the motor shaft spins freely. Next, check for line voltage at the brown and black wires. Remember, the contactor does not switch the line voltage for these motors, it's always hot. Then, verify you have a 24-volt AC call between Y and B on the fan control board. From there, you will monitor the red LED status and track the DC communication voltage from terminals A and C all the way out to the blue and yellow motor leads. We will look closer at how these outdoor motors change speeds next. Picking right up with our motor models, let's take a look at the ECM1 motor. This was an earlier iteration in the ECM lineup. As you can see from its design, it features a robust base with cooling fins to manage the heat generated by the internal electronics. The control module is integrated directly into the base, which was a significant step forward in motor technology at the time, allowing for more precise control over the motor's operation compared to traditional PSC motors. Now, let's dive into troubleshooting cooling airflow issues on the ECM2, specifically when the correct airflow cannot be obtained and the CFM LED isn't flashing correctly. Step 1 is to verify your low voltage inputs. You need to check for 24 volts AC between the common terminal B and the fan terminal G, as well as between B and the cooling terminal Y. If you have voltage and the red Y LED is illuminated, you can proceed to the next step. If you don't have voltage here, the motor isn't receiving the pull to run, which means your fault lies upstream in the thermostat or the thermostat wiring. If step 1 checks out, step 2 asks if the red BK LED is on. Note that only certain control boards like the CNT01654 have this LED. If it is on, you skip ahead to step 5. If it's off, or your board doesn't have one, proceed to step 3. Step 3 involves checking for 24 volts AC between terminals B and BK. This circuit is crucial for humidistat or ramped cycle operation. If a humidistat is installed and its switch is open, cooling airflow is intentionally reduced by 20% to help dehumidify the space. If you don't have a humidistat, a jumper must be installed between R and BK to ensure full airflow. Moving to step 4, we shift our focus from the control board terminals to the 16-pin low-voltage control plug right at the motor. You need to check for positive 4 volts DC between pin 10, which is the humidistat input, and pin 3, which is common. If you have this voltage but airflow is still high when the humidistat opens, or the ramped cycle fails, you'll move to step 5. If you don't have the 4 volts at the motor plug, you must check for it back at the control board. Finding it at the board but not the motor means your 16-wire harness is faulty. If it's missing at the board entirely, the board itself needs replacing. Step 5 checks the humidistat or ramp cycle enable signal. You're looking for 24 volts AC between pin 9 and pin 3 on that same motor plug. There's an important exception here. On packaged gas electric units, this voltage must be 0 for these features to operate. If the voltage is correct, the plug is secure, but the CFM won't drop when the humidistat opens, the motor module is likely defective and should be replaced. Again, if the voltage is missing at the motor but present at the control board, your wiring harness is the culprit. If your airflow is simply incorrect, step 6 has you check the cooling blower speed signal. This requires measuring for positive 4 volts DC between pin 14 and pin 3 on the motor plug. This DC voltage is the communication signal telling the motor to run at the designated cooling speed. Just like the previous steps, if the signal is absent at the motor, trace it back to the control board to determine if the issue is a broken wire in the harness or a failed control board. Step 7 is where we verify the programming. Cooling airflow is determined by dip switches 1 through 4. Switches 1 and 2 set the tonnage and send signals via pin 5. Switches 3 and 4 set the CFM per ton and communicate via pin 7. You need 24 volts AC at the board for this test. By turning one switch on at a time, you should read specific DC voltages at the motor plug, positive 12 volts for switches 1 and 3, and negative 12 volts for switches 2 and 4. If the voltages are correct but the green LED isn't flashing properly, we move to the final step. The final check, step 8, looks for conflicting signals. You need to measure for any voltage, AC or DC, between terminal B and the heating terminals W1, W2, or W3. If you read 1.5 volts or higher, the motor is receiving a call for heat at the same time as cooling. Because ECM2 motors prioritize the highest requested airflow, or specifically the heating airflow in gas furnaces, this phantom voltage will override your cooling settings. If voltage is present, the fault is in the thermostat or wiring. If no voltage is present and the airflow is still wrong, the motor module must be replaced. Shifting gears, let's examine the CTM high-efficiency motor. This motor utilizes ECM technology, but without the complex matrix of programming options found in the ECM2. It behaves somewhat like a traditional PSC motor. As static pressure increases, airflow goes down, and as RPM increases, amperage goes down. However, it maintains high efficiency by using a brushless DC permanent magnet rotor and a power control module that creates three-phase voltage from a single-phase line. Its defining characteristic is that it focuses on maintaining constant torque using a simpler interface with pre-programmed 24-volt AC input taps. When wiring the CTM high-efficiency motor, you'll use 3/16-inch male quick connect terminals for the line voltage. The connections vary depending on the application. For gas furnaces operating on 120 volt AC, you connect line to L, ground to G, and neutral to N. For air handlers operating on 230 volt AC, L becomes line 1 and N becomes line 2. In the 230 volt application, the G terminal on the module is not used. Instead, the motor is grounded directly to the end bell. Air handlers utilizing the CTM motor often incorporate an electronic time delay relay, or ETDR. This is a solid-state control board designed to provide a 45-second timed off delay for the blower. The heart of this board is a double-pole double-throw relay, designated as K1. When energized, the normally open contacts of the K1 relay close to control two specific outputs: the J circuit, which acts as an electric heat interlock, and the 24-volt AC G output that signals the CTM motor to run. Out of the box, the ETDR is wired so the delay option is inactive. In this factory configuration, voltage from the thermostat G terminal hits both T3 and T7, closing the K1 contacts. When the thermostat demand stops, both circuits immediately de-energize. To actually enable that 45-second timed off delay, you must modify the wiring. You disconnect the T3 wire from the G circuit and move it to the R, or constant 24-volt circuit. This way, when the thermostat removes the G demand from T7, T3 remains adding the K1 relay closed and keeping the motor running for an additional 45 seconds to extract residual heating or cooling. 4 distinct input commands can be sent to the motor's computer using the first 2 dip switches on the control board. If only switch number 2 is closed, it sends an in-time command, and the motor runs its factory program for that state. If both switches 1 and 2 are closed, a double time command is received. Closing only switch 1 results in an out-of-time command. Finally, if both switches are left open, the computer receives a no command input and defaults to its standard factory program. When the ECM2 receives multiple calls simultaneously, how does it know what to do? It operates on an airflow priority system. Generally, it will run at the highest speed call it receives. For instance, if it gets calls for continuous fan, cooling, and first stage heat all at once, it prioritizes the higher demands of cooling or heating. However, there is an exception. In a gas furnace application, the heating calls, W1 or W2, will always take absolute priority over a cooling Y call, regardless of which speed is technically higher. Let's break down the terminal pins on the control board. The BK terminal is typically the humidistat input, though on variable speed systems it acts as the PWM blower speed command. W1 and W2 control the airflow for low and high heat, respectively. The G terminal is the standard fan on or off command, which defaults to 50% of the programmed cooling airflow. Y low handles the low-speed cooling airflow for 2-speed or 2-compressor systems. Continuing with the terminals, G1 is specific to package units and calls for 100% cooling airflow. The Y terminal is your standard high-speed cooling call. The CFM terminal is the output that flashes the LED to indicate the programmed airflow. B is your 24-volt AC common, while R provides the 24-volt AC power and timing reference. Finally, the O terminal enables the cooling cycle humidistat on single or 2-speed systems. Now, let's look at what each pair of dip switches actually programs. Switches 1 and 2 set the tonnage of the outdoor unit. Switches 3 and 4 fine-tune the airflow, allowing you to select 350, 400, or 450 CFM per ton. Switches 5 and 6 configure the indoor blower time delay at the end of a cooling cycle, which can also affect the heating off cycle depending on the equipment. Lastly, switches 7 and 8 set the specific airflow for low and high heat. For enhanced comfort, you can enable ramped operation by turning dip switches 5 and 6 on. This provides a gradual ramp up and ramp down of the blower, requiring a simultaneous call on Y and G. If you are integrating a cooling humidistat, it is enabled when the motor computer receives a call on the O terminal. Remember, for cooling-only units, you must install a jumper between Y and O, and you must cut the factory jumper between R and BK to properly connect the humidistat. When troubleshooting heating airflow issues, start by checking the green CFM flash rate for both low and high heat. If the flash rate is correct, but the motor is cutting off or the airflow feels low, the issue might be high total duct static pressure causing the motor to throttle back. If the flash rate is incorrect, your next step is to grab your multimeter and check for 24 volts AC between the B terminal and W2 or W3 on the low voltage motor control board. If you don't have voltage at W2, check for 24 volts AC between B and W1. If voltage is missing here, the fault is likely in the thermostat or its wiring. If voltage is present at the board, move to step 4 and check for 24 volts AC directly at the motor's low voltage control plug, specifically between pin 2 and the common pin 3. If you have voltage at the board but not at the motor plug, your 16-wire low voltage harness is faulty and needs repair or replacement. Step 5 involves checking for 24 volts AC between pin 13, which is the high heat speed, and pin 1 on the motor plug. If that checks out, step 6 tests the heating airflow programming switches, numbers 7 and 8. These communicate with the motor via pin 11. By turning switch 7 on, you should read positive 12 volts DC at pin 11. Turning switch 8 on should give you negative 12 volts DC. If these voltages aren't present at the board's output, the control board itself is defective. For step 7, check if there is any voltage, AC or DC, between B and Y low or Y. If you read 1.5 volts or higher, the motor might be confused and delivering cooling airflow instead of heating. You should also check the motor winding resistance. All 3 legs should read the same. Finally, step 8 involves jumpering the G in to G out pins on the ignition module. If the motor suddenly runs when you do this, the ignition module is the culprit and must be replaced. Shifting focus to the CTM high-efficiency motor, the low-voltage connections utilize quarter-inch male quick-connect terminals. The C terminal is your 24-volt AC common. Taps 1 through 5 are inputs for 24 volts AC. It's important to note that tap 1 is always programmed from the factory. However, if you apply 24 volts to a tap that hasn't been programmed for that specific unit's application, the motor will simply not rotate. When looking at a typical furnace wiring diagram for these high-efficiency motors, you'll be dealing with an integrated furnace control, or IFC board. These are shipped from the factory with the cooling off delay set to 0 seconds, which corresponds to switch S1 being in the on position. If you need to actively ensure the 0-second fan off delay option is utilized based on your specific setup, you actually move that switch to the off position.
Now let's examine the 6-wire variable speed outdoor fan motor. On cooling models, this is a 2-speed ECM controlled by the indoor thermostat's Y-call and an outdoor thermostat, known as ODTA. When the indoor thermostat sends 24 volts AC to the motor's yellow wire, it runs on high speed. To switch to low speed, the outdoor thermostat applies an additional 24 volts to the white wire. This switch to low speed happens when the outdoor temperature drops to 76 degrees, and it reverts to high speed at 80 degrees.
On heat pump models, the operation is quite different. The outdoor fan motor is controlled by the unit's defrost control board, which outputs a direct current pulse width modulation, or PWM, signal to the motor's yellow wire. You can read this with a standard voltmeter. A high-speed command is a 79% PWM signal, reading about 15 volts DC. A low-speed command is a 29% PWM signal, reading around 6 volts DC. We will explore how to troubleshoot these specific PWM signals in the next segment. Let us look at the theory of operation regarding motor speed. The speed of an ECM is fundamentally tied to its physical construction and the frequency of the alternating current. For instance, a 2-pole motor has a pole distance of 180 degrees, making one full cycle a 360-degree distance. In contrast, a 4-pole motor has a pole distance of 90 degrees. To calculate the synchronous motor RPM, you multiply the AC frequency in hertz by 120, and then divide that by the number of poles in the motor. As the motor's revolutions per minute increase, the motor impedance, which is measured in ohms, also goes up. Conversely, the motor torque goes down as the RPM increases, and at synchronous speeds, the torque is actually minimal. The difference between that synchronous RPM and the rated motor RPM is known as slip. Ultimately, the motor speed is varied by intelligently changing the power and frequency applied to it. Seriously, when performing a quick check on a motor that will not run, there is a golden rule you must never break. ECMs cannot be tested unless they are under load. Attempting to test these motors without a proper load will yield inaccurate results and can potentially cause issues. If the blower motor will not run, begin by jumpering the 24-volt AC R terminal to the G terminal on the low voltage board. If the motor runs, your issue is likely the thermostat or its wiring. If it does not run, proceed to step 2. Unplug the 16-wire low-voltage harness from the control board and jumper 24 volts to pins 12, 15, and the common pins 1 and 3. If it runs now, the motor control board needs replacing. Moving on to step 3. Bypass the harness entirely by jumpering the 24 volts directly to the motor's low-voltage plug pins. If it runs, the harness is faulty. If not, go to step 4 and verify your line voltage. Furnaces require 120 volts with a jumper between pins 1 and 2, while air handlers require 220 volts. You should also check the motor winding resistance. All 3 legs will read the exact same resistance, just like a 3-phase motor. For gas furnaces utilizing specific ignition controls, there is a 5th step. You'll need to plug the 16-wire harness back in and jumper the G-in pin to the G-out pin on the White Rogers module. If the motor runs, the ignition module is the culprit and must be replaced. If it still does not run, move the jumper to the metal part of the plug to check for bad pin contacts. When utilizing a troubleshooter kit, which typically includes a specialized circuit board and a 4-wire test cable, remember that the motor and module must be treated as a single unit. You'll be verifying that the correct high voltage, either 120 or 240 volts, is present, alongside the 24-volt low-voltage signal. Transitioning to outdoor units, the 5-wire ECM outdoor fan motor has specific troubleshooting paths depending on the symptom. If the motor will not run at all, you follow the first diagnostic chart. If it runs but will not change speeds properly, you use the second chart. And if it is erratically changing speeds without a thermostat command, there is a specific step in chart 1 to address that. For 6-wire ECM outdoor fan motors, always remember that high voltage is present whenever the outdoor unit's disconnect is turned on. Your first step is to ensure the motor shaft turns freely by hand, keeping in mind it will feel slightly different than a standard motor. Next, verify the line voltage past the polarized plug is within 10% of the nameplate rating. To test the low voltage side of a 6-wire motor, apply 24 volts AC to the yellow and blue wires. The motor should start. Then disconnect the yellow and apply the voltage across the yellow and white wires, keeping blue as common, to test the low speed. Note that on heat pumps utilizing a pulse-width modulated DC signal for defrost, the white wire is not used, meaning only 5 wires connect to the motor. That brings us to the end of our comprehensive look at ECM motors. Let us quickly recap the most critical takeaways. Always test these motors under load. Systematically verify your high voltage and low voltage signals, and check that winding resistance is equal across all 3 legs. By isolating the harness, the board, and the motor, you can accurately pinpoint any fault.